Hey guys, I know you've missed calculus, so let's get straight to it. Find the derivative. Y equals the natural log of x squared over 3x minus 2. Now the hard way would be to do a quotient rule within a chain rule. The easy way would be to rewrite the natural log first, which is the first thing you practice on your homework is rewriting natural logs. So let's apply that here. I can rewrite a quotient as a difference. I can rewrite this as the natural log of x squared minus the natural log of 3x minus 2. I can even take that one step further. I can take this power and move it out front. So I can rewrite this as 2 natural log of x minus the natural log of 3x minus 2. Now this looks much more pleasant to take the derivative of y prime equals, that's just a coefficient, so I'll carry on that too. And the derivative of the natural log of x is just 1 over x minus, and then the derivative of the natural log of a function then is just that function on the bottom with its derivative on top, following that pattern of u prime over u, where this is u. And that's it, I'm done. All I have to do now is make that pretty. Y prime equals 2 over x. That was really the only other thing I could do to simplify. And it's done. Let's do another one. Find the derivative. And once again, this looks a bit complicated. I don't want to take the derivative of that yet. I could do a giant quotient rule with chain rules, but I could also rewrite this and make my life easier. So I can start by rewriting that square root as a power. So that's x squared plus 1 over x squared minus 1 to the 1/2. And then I can take that 1/2 and move it out front. That'll be much more pleasant to deal with. So I have 1/2, and then this quotient I can rewrite as a difference. So this will be the natural log of x squared plus 1 minus the natural log of x squared minus 1. I can distribute the 1/2. And then I've got a nice function that I can take the derivative of. So when I go to take the derivative, my 1/2 carries along, and then it's 1 over my function, so the first one was x squared plus 1, with the derivative on top, minus 1/2, and then derivative of the natural log is 1 over the function multiplied by its derivative on top. I can simplify that just a little bit. 2's will cancel here, and so I can say this is equal to x over x squared plus 1 minus x over x squared minus 1. Done. Let's do another one. Find the equation of the tangent line at the point 1, 2. And I have x cubed minus the natural log of x over e. Again, before I do anything, I'm going to rewrite this natural log. I'm going to say y equals x cubed. This is a quotient. I can turn that into a difference. That's the natural log of x minus the natural log of e. And the natural log of e is just 1. That's equal to 1. I'm going to distribute this negative. Y equals x cubed minus the natural log of x plus 1. Now I'm ready to take the derivative. So y prime is 3x squared minus the derivative of natural log of x is just 1 over x, and the derivative of a constant is 0. Now at this point I want to use my point to find the slope of my line at 1. So I'm going to plug in y prime of 1 will be equal to 3 times 1 squared minus 1 over 1. That's a 1. So that's just equal to 3 minus 1, which is 2. There's my slope. My point was 1, 2. So now I can do point slope form. Y minus the y value equals the slope times x minus the x coordinate. And we can clean that up, make it y equals mx plus b. So y equals 2x minus 2 plus my 2 from the left. Those cancel out, and I end up with y equals 2x. There's my tangent line. Piece of cake. Let's do an implicit differentiation problem now. Find dy dx of the natural log of xy minus 3x equals 4. I see that I've got a product rule inside my natural log there. I could do a product rule, or I can rewrite my natural log. Seeing that pattern over and over again. That's a product, which means I can rewrite that as a sum. And then taking my derivative of both sides becomes easier. Derivative of natural log of x is just 1 over x, plus the derivative of natural log of y is 1 over y, but I gotta follow my chain rule, dy dx, minus 3 equals 0. And then remember your routine here, collect all your dy dx terms on the left, move everything else to the right. 1 over y, dy dx equals 3 minus 1 over x. And then I will multiply both sides by y to get dy dx by itself. So I have dy dx equals, and I can distribute that y. I can say that that's 3y minus y over x. And it's done. One more, because I know you all missed these videos over Christmas break. Find any relative extrema and points of inflection, y equals natural log of x minus x. I know my routine for finding relative extrema is I have to find my critical numbers, which is where my derivative is equal to 0. So we'll start by finding the derivative. Y equals 1 over x minus 1. Set that equal to 0 and solve for x. So 1 over x equals 1, x equals 1. And then I can set up a table for myself here where x equals 1 is my critical number. And when I'm choosing values to test, I need to make sure they're in the domain. Remember, you can't take the natural log of a negative number or 0, so that's not very helpful. So I'm going to choose f of 1/2, and then something on the other side, we'll try f of 2. If I plug 1/2 into this function, you'll get, let's see, oh no, I'm plugging that into the derivative. Catch my errors there. If I plug 1/2 into this function, I'll get 2 minus 1, which is 1. It's a positive number, so my function is increasing until I get to x equals 1. If I plug 2 into this function, I'll get 1/2 minus 1, which is negative 1/2, and that is decreasing. And so if my function is increasing and then decreasing, this is a relative max at the value of x equals 1. If I plug 1 into this equation, I'll get 0 minus 1, which is negative 1. So my point is I have a relative max at the coordinates 1, negative 1. Now the question also asks for any points of inflection. I know that is where the second derivative is equal to 0. So I'm going to start with my first derivative. Y prime equals 1 over x minus 1. And I want to take its derivative, so I'm going to rewrite this as x to the negative 1 minus 1, so I can do my power rule. And so my second derivative will be negative x to the negative 2 minus 0. I can say that that's negative 1 over x squared, and I want to see where that is equal to 0. And you can see that if I cross multiply here, I'll get that negative 1 is equal to 0, which is a false statement. which means that this is never equal to 0. So there are no points of inflection. And if we wanted to verify that, we could go graph our original function. If I graph my original function, I see that it starts here, goes up, and then goes down. And so sure enough, there is my relative max at the point 1, negative 1. And you can see that it's always concave down. There's never a change in concavity. And so it makes sense that I would get